power. Let's talk about the future. Power! It's what we all want. It's what we all need. But not the ultimate power kind. I'm talking about portable power for our devices like phones or cars or any of our other gadgets. See, when we're on the go, we can't always plug into a wall outlet to get our power. I'm Grant Imahara, and I'm here at UCLA to talk to Dr. Rick Kaner, who's made a breakthrough in portable power. Hi, Dr. Kaner, I'm Grant. Good to meet you.
Good to meet you.
So, I've heard that you've made a breakthrough in portable power. What's the nature of this breakthrough?
Well, we began working on graphene, which is a single layer carbon, and it turns out it can store a tremendous amount of energy.
Oh, like a battery.
Like a battery, but not quite. We're working on something called supercapacitors. So all the charge is stored on the surface. And if you have an enormous surface, you can store a lot of charge very quickly.
Currently, carbon-based supercapacitors are used for electric buses in China. And the idea is you just make a charging station, the bus stop, every 5 or 10 miles. And as people get on and off the bus gets charged. So you can do that within a minute to 2 minutes. You could stick them into your cell phone and charge your cell phone in 30 seconds or less.
Graphene is a single layer carbon. So if you look at this is graphite. So
Okay.
graphene's the top layer. You can look at the natural mineral graphite. This is how graphite comes out of the ground.
It's actually really light. It's much lighter than it looks.
It's not that dense.
Yeah.
Graphene, a single layer, was discovered by Novosel and Geim in 2004, but I actually started on graphene much earlier than that. In 2002, we took out a patent, we believe the world's earliest patent on how to make graphene.
Yeah.
And so we developed a method where we take graphite, we oxidize it, turn it into graphite oxide, and we're going to show you how we can use a laser and deoxygenates, it turns it into graphene.
So that's why you have all of these CDs around the lab. It's not that you listen to a lot of music.
No,
This is what you're using to make the
that's
graphene.
what we use to make the graphene.
Okay.
Now, let me introduce you to my student, Dr. Maher El-Kadi, who's developed this process.
All right. Okay, so you're going to do a demo here of how you make graphene.
Yep. You will have to just get the GO layer on the CD. To do that, you have to do this on a piece of plastic. And
This is like a science cooking show.
and then the next step will just to dry this up. You can just put it in an oven.
Okay, cool. Let's do it.
Now I need to put it on a CD here.
Okay, looking good.
All I'm gonna do is convert the GO here to graphene. And to do that, I'm just using a simple label maker.
You use a label maker
Yeah,
to make the future?
Yeah.
Because you use whatever tools are at your disposal.
Yep. So what we're doing is coating this material on t-shirts and then making them into graphene supercapacitors for wearable electronics.
Really? So it can light up, it can store power for my phone.
Yes.
Well, that's awesome, Maher. Thank you very much.
Yeah, anytime.
All right. And now we have John Nelson, president of TDK Americas, to give us another perspective on power conversion from one of our supplier partners. Hey, John. So I imagine you must meet a lot of engineers on a daily basis. What are some of their concerns relating to power and power management?
The main concerns we hear from engineers are basically converting more and more power into smaller packages or smaller footprints.
Yeah. What trends do you see happening in power management and conversion?
The trend is to push switching frequencies to higher and higher levels. This opens the door to lower capacitance and inductance,
Awesome.
reduces size and power loss while increasing overall performance.
Cool. So when do you think new materials such as gallium nitride are going to become part of mainstream power conversion? And what's been the delay so far?
Well, gallium nitride is on the way. The advantage of gallium nitride is that it can switch about 1,000 times faster than standard silica. So once the cost comes down and the reliability is established, we're going to see more of it.
All right, thanks for your time. Hey everybody, I'm talking to Infineon, one of Mouser's supplier partners. Hey Adam, What are the future materials for the power of tomorrow?
We are incredibly confident that gallium nitride will unlock the next level system efficiencies, energy savings, power density, as well as overall system cost.
Wow. Now what trends do you see and how is Infineon working towards them?
There are two underlying trends. First of all, the higher efficiency, and second of all, to support the density requirements. Let's take the density requirements. It's fascinating to watch, but in the switch mode power supply for servers, their requirements is to achieve more output power for the same size. Now let's look at the other extreme for flat panel displays. They are requiring the same output power, but for smaller size.
Cool. That's a man who knows the future. What makes the graphene ideal as a supercapacitor?
The real exciting discovery came when Maher dragged me into the lab, and he said, take a look at this. And he just took a light bulb and he just turned it on with this little piece of graphene. But the amazing thing is, it doesn't stop working. After charging for 2 or 3 seconds, he ran this light for over 5 minutes. I thought we have something very important. I thought the world changed at that point.
It's truly amazing to be able to take a peek into the future and see how all these advancements in energy storage and power management are going to be keeping us connected, going to be keeping our devices powered, our cars, and even our homes. So special thanks to Rick and Maher and all the people working with their discoveries. I'll see you next time.